And our last speaker of today is Alex Dugas, who will speak about semi-simple homology resolutions of modules. Sorry.
All right. Yeah, thank you. So, and thanks to the organizers, of course, for, setting up this great conference and giving me the opportunity to speak here. I have to say, this is actually my first online conference presentation, so hopefully it will go okay. And so let me share my screen. All right, so this is joint and ongoing work with Ben Briggs and Shrikant Iyengar. It started a couple of years ago, but we're sort of in the process now of trying to polish it up, and hopefully it will be up on the archive, perhaps later this month. That would be my hope. But so here is a preview of what we've been considering. And so just to start, A will denote always a right Noetherian ring. I'll write mod A for the category of finitely generated right A modules. And our motivation is to basically generalize finite projective resolutions. So as I'm sure you're all familiar with this, finite projective resolution is just a complex, as we see here. So, just where each of the terms P sub I is a finitely generated projective module. And also we require this complex to be exact. So, so there are a couple of options for generalizing such a resolution. One possibility is that we relax condition 1. And so in this case, we get resolutions by non-projective modules or by other modules. And this is actually something that's been studied quite extensively. So for example, we see such types of resolutions in the context of relative homological algebra, in particular representation dimension. Gorenstein dimension is another setting where we see such resolutions. We also have this recent work of Baumer and Gallower on permutation resolutions over group algebras. And we might also mention that sort of these types of resolutions come up also when we're considering non-commutative resolutions of singularities. So but the point is that, this type of generalization of projective resolutions has been studied quite extensively. The other option, which is really what our focus will be here today, is if we relax condition 2. And this leads to the notion of non-exact resolutions by projectives. And we might put resolutions in quotes there or something. And so here, I'm not aware of very many instances where this type of generalization has been studied, but really the one we're focused on, and this was introduced by Benson and Carlson way back in '87. And so here they allow such resolutions which have semi-simple homology groups. And they call these completely reducible homology resolutions, or CRH resolutions for short. And another more recent example, this is in the work of Gaby, David Jorgensen, and Takahashi. So they allow homology in add M. So, or the homology actually summands of copies of M, where M is still the module being resolved. And this leads them, or they call these quasi-projective resolutions. So there is a little bit of overlap between these two notions, sort of in the context where you have a simple module over a local ring. But for the most part, these are fairly distinct types of resolutions. Okay, so as our focus is really going to be on these semi-simple or resolutions with semi-simple homology, which we've renamed semi-simple homology resolutions. I should mention that a lot of our terminology here is still somewhat in flux and may eventually change, but if we can think of better terminology to use. So let's see. All right, so now so let me state our definitions, and we'll look at some examples and questions that arise. So first thing, I want to just write down a definition of a semi-simple homology resolution, and we call these SSH resolutions for short. And we can state the resolution quite easily, not just for modules, but for complexes. So let M be a complex in the bounded homotopy category of mod A. And so a semi-simple homology resolution of M is going to be a map called epsilon from a complex P to M, such that, and sort of three things have to be true. First of all, we want P to be perfect, a finite bounded complex of projectives. Second, we want H epsilon to induce isomorphisms in homology in all degrees where M has homology. So denote this for all I less than or equal to the sup of M. The sup of M just means really the largest degree in which M is non-zero. And thirdly, that HI of P is allowed to be semi-simple, which could mean it does include zero for all I greater than the sup of M. Right, so this would, if of course we regard modules as complexes sort of concentrated in degree zero. And so this includes the notion of SSH or CRH resolutions that Benson and Carlson consider. Okay, so let's look at some simple examples. So first of all, if M has finite projective dimension, well then of course a usual projective resolution of M will work. Second, we have a couple of trivial examples, which are important to realize. But if P is a perfect complex, then we can actually just take the identity map. And sort of this is trivially an SSH resolution. Of P. Another trivial case is if we start off with an acyclic complex M, then the zero map is an SSH resolution of M. So the fact that perfect complexes and acyclic complexes have these trivial SSH resolutions, it will be important because it basically means that we can work in the derived category or in the stable derived category or the singularity category if we want. And sort of another class of examples. So if we just have a module M where the nth syzygy omega n of M is semi-simple, then we can take a truncated projective resolution, so stopping at Pn minus 1. And then one last example that's sort of very common in commutative algebra is given by the Koszul complex. So if we have a commutative and we take a maximal ideal M, generated by x1 through xr, then the Koszul complex has homology annihilated by M, and hence has semi-simple homology groups. So if we look at this natural map from the Koszul complex to A over M, this is an SSH resolution. All right, so those are some simple examples. Let's turn now to some natural questions that we can ask about these resolutions. Sort of the first set of questions. I'll actually talk about existence questions first. So, right, so naturally we want to know for which algebras or for which rings A or for which modules or complexes M do SSH resolutions exist. And maybe more importantly, kind of too, what are they good for? So, if what are the consequences for A or for module M of it having an SSH resolution? So, And sort of there's one other sort of somewhat embarrassing question, which I should include here too. Something that, it's embarrassing that I don't know the answer to this yet, but so far we have, we'll talk about some existence theorems that we've been able to prove, but so far we don't know of any examples, say over a finite dimensional algebra, of a module that does not have an SSH resolution. So is there a finitely generated module MA, let's say over a, just say like a finite dimensional algebra? And I feel like here there should be, plenty of examples that are not too exotic. However, it doesn't appear easy to prove that a given module does not have an SSH resolution. So I think that we need to develop more methods for tackling those types of problems. And a second batch of questions we can look at, these are perhaps more interesting, but also they seem to be a bit harder. So these deal with the structure of SSH resolutions. So if M has an SSH resolution, we can ask, we can look for minimal SSH resolutions, and there's a couple of different notions by what we might mean by that. So we can ask, what is the minimal length of an SSH resolution of M? And just by length here, I just mean sort of the number of terms in the complex, just like what we normally mean by the length of a projective resolution. And I should stress here, just by definition, SSH resolutions are always finite by definition. Or we can also ask, what is the minimal length of the homology? So, I mean, in other words, sort of how many simple modules appear in the homology groups of an SSH resolution of M. And so it was actually this type of question here, which I think was, led Benson and Carlson to introduce this notion of semi-simple homology resolutions. So what do I want to say here? I mean, so they were interested in in finding restrictions on finite groups that could act freely on direct products of spheres. And I mean, so they came up with a conjecture really a lower bound for this total length of this homology. So for SSH resolutions of the simple module K over a group algebra, and in fact, I think here G is a elementary abelian P group. And if their conjecture held, then it would imply some conjecture about elementary abelian P groups acting freely on products of spheres. However, that their conjecture turns out to not be true So this was disproved by recent work of Shree and Mark Walker. So they give examples of complex finite complexes of projectives with where the total length of the homology is relatively small. So all right, so these structural questions are interesting, but again, there's a lot we don't know there. It seems very hard to answer those. But even in cases where we know that SSH resolutions exist, for the most part, our proofs of existence don't really give us a lot of insight as to how long the minimal SSH resolutions are going to be, or what we can say about their minimal length of their homology. So all right, so let me move on and talk about these existence results now. And if you've read the abstract, these are stated there, so it's not too much of a spoiler. Let me point out that I think here I wanted K should be an algebraically closed field. Just to make these statements a little bit easier. And so in the following cases for these rings A, we know that every finite length A module has an SSH resolution. And so the first result here is just the result of Benson and Carlson. This is when A is a group algebra with a G a finite group and K a field. Of course, if the characteristic of K does not divide the order of the group, this would be trivially true because our group ring would be semi-simple. So this is really mostly of interest when the characteristic of K does divide the order of the group. And then for our results, so the first one that I'll state here is for finite dimensional algebras with the FG condition. And so this is really this of course includes all of these group algebras. So let me recall what FG means. It means that the Hochschild homology of A is Noetherian. And if we look at X star, well, really X star of any two modules, but it suffices to look at A modulo its radical J. This is finitely generated as a module over the Hochschild cohomology ring. So J is just the radical of A. All right, so then, so next, in order to find some examples of algebras that do not satisfy the FG condition, we looked at algebras, self-injective algebras of radical cube 0. Right? And so this is the second class of algebras where everything has an SSH resolutions. Right, so we show that the FG condition is not necessary. And then finally, sort of the last class is any commutative ring at all. So this is something else I wanted to say here. So, but we point out that, so this is, well, again, A is still a Noetherian ring, so we're looking at commutative Noetherian rings, but still it's only establishes existence for finite length modules over commutative rings. And if we want to look at finitely generated modules instead, then in this case, one restriction on the ring is necessary. So if every finitely generated A module has a SSH resolution, it's pretty easy to see that A must be an isolated singularity. And we're able to show one result in the opposite direction for isolated singularities. So let me just mention this. So here, if A is a local Gorenstein, isolated singularity, then every finitely generated A module is at least a direct summand of a module with an SSH resolution. So it seems hard to remove this restriction that this direct summand. It seems hard to remove this direct summand condition. So so it's not clear if every A module, every finitely generated A module has an SSH resolution in this case, but at least everything is a summand of something that does. Okay, and basically the proof of that basically uses the fact that we can get, in this case, every we can, by taking sort of suitable syzygies of finite length modules, we can get all of the maximal Cohen-Macaulay modules, and then any other finitely generated module has a syzygy, which is also a maximal Cohen-Macaulay module. All right. Okay, so let's see. So now I'll say some things about the proofs of these results. And sort of first off, the general strategy is the same for all cases pretty much. And this was basically the strategy that Benson and Carlson used. And so they sort of first show that the simple modules have SSH resolutions. And then they kind of build SSH resolutions for other modules by taking extensions in a sense. And so this first step, this turns out to be kind of different, ad hoc constructions in each case. However, the second part of this is a bit non-trivial, but it's very general. So this works. This is basically the same process in all of the cases. And so I want to say some remarks about that first. And so one of the problems with, if you have two complexes with semi-simple homology, and you kind of take some extension of them, like in the homotopy category, you have a long exact homology sequence, and the homology of the extension could be an extension of semi-simple modules, so it might not be semi-simple anymore. So in order to get around that, we introduce the definition. And so let's say that a complex M is highly SSH resolvable if so for all n, and I'll just say greater than or equal to 0, n just has to be sufficiently large, we can find an SSH resolution of M, call it epsilon. This is going to be a different resolution for each M, such that if we look at the cone of epsilon and take its homology, this is 0 for all I less than or equal to n. So in other words, what's happening here is that we're looking at basically this SSH resolution P, initially coincides with the usual projective resolution for M. So up through degree n, let's say, and then after that, it can have some non-zero homology. Okay. And so we can look at the subcategory of all of these highly resolvable complexes, and I'll call this HR of A. So this is just all of the M. The homotopy category such that M is highly SSH resolvable. And so this is of course, a subcategory of the homotopy category, but it also induces subcategories of the derived category. And of the singularity category, which is the quotient of the derived category by the category of perfect complexes as well. And so the theorem that we can show is that, in fact, this is a triangulated subcategory of whichever one of these categories we want to consider it inside of. Right, so however, there's one kind of annoying problem with this, one thing we don't know. And I'm not even sure to expect that it's true, but we don't know if this is a thick subcategory. So we don't know if it's closed under summands. So this is kind of an annoying issue that sort of repeatedly comes up. And that's part of the reason why in the isolated singularity case, we can't say whether every module actually has an SSH resolution itself. Okay, and so now just as a corollary from this, we get the the following sufficient condition. So if every simple A module is highly SSH resolvable, then so is every finite length A module, or even any bounded complex of finite length modules. All right, and that's all right. So how am I on time? Okay, so basically that half of the proof is going to be the same in all of the cases where we prove existence of SSH resolutions. And that means that the first step is to show that every simple A module is highly SSH resolvable. And that's equivalent to saying that every syzygy of every simple module has an SSH resolution. So I'll quickly sketch some of the arguments that we use in a couple of these cases. So first, when we have an algebra satisfying the FG condition, so we can start by taking, we know that our X star of A mod J with itself is finitely generated over the Hochschild cohomology. So that means we can find a finite homogeneous system of parameters for it, consisting of homogeneous elements zeta 1 through zeta d in the Hochschild cohomology. And by taking suitable powers of these zeta i's, we can control their degrees. So what we're going to want, what we're going to want here is, if we're given an integer n, we want n to be less than d1, and then for each of the additional di's, we want di to be greater than the sum of the degrees preceding it. And that's going to allow us to space out the homology groups in the complex that we construct. And so now if we have a simple module S, we can start off with this L0 be this complex S in the bounded derived category. And we can define these further complexes inductively. So, this is Li is going to be sort of the co-cone of the induced map given by zeta I from Li minus 1 to the dith suspension of Li minus 1. So this is a triangle. And so in fact, we could, another way of describing this is that Li is the desuspension of this causal object induced by zeta I. And so carrying out this process, this means that once we get to xd, so once we go through all of these zeta i's, our complex LD will have extensions annihilated by powers of every zeta I. And basically this means that it has trivial variety and it is going to be a perfect complex. So at the same time, we can use sort of the long exact homology sequence applied to each of these defining triangles to really control which degrees the LD has homology in. So the homology groups of LD are going to be equal to, they're all going to be in add S. And they're all going to be 0 for all I less than or equal to n. So in fact, this means that our LD is going to be an SSH resolution for S, which is initially exact for this n here is an arbitrary integer. So it follows that S belongs to this subcategory of highly SSH resolvable modules. Okay. Yeah, and so that works for each simple module S, and therefore every finite length module will also have an SSH resolution. Okay, next, for the case where A is commutative, the idea there, as we saw before, is to use the Koszul complex. We know that this gives an SSH resolution for the simple module A over M. But the problem then is, how to extend this to SSH resolutions that are initially exact. So these will be that begin exact. And so the trick here is to regard this Koszul complex as a DG algebra. And then we can take a semi-free resolution of A mod M of the simple module. Think of it as a DGK module. And this is a quasi-isomorphism here. And then by looking at a DG submodule of F, generated by basis elements of degree less than or equal to n, so this will be a finite complex of free A modules, and it will have, its homology will be a module over the homology of K, which is annihilated by M. So if we call this map epsilon, so then we can show that the restriction of epsilon to Fn is an SSH resolution that is exact in degrees less than or equal to n. And so again, this shows that the simple module A over M is highly SSH resolvable, and thus so is every finite length module. Okay, so I just have a few minutes left, so those are just quick sketches of the proofs in two cases. The radical cube zero case is just uses sort of a very explicit construction of these SSH resolutions of the simples in terms of a quiver with relations. So it's I'm not going to talk about that now, but there are a couple of other interesting facts which I'd like to point out. So first of all, if we have an Artinian algebra and we know that all finitely generated A modules have SSH resolutions, then there exists a number n that really gives us a uniform bound on the lengths of these SSH resolutions. So it's such that every MA has an SSH resolution of length less than or equal to n. And so that can be proved, for instance, by induction on the Lovie length of a given module. And one other thing I'd like to mention is that if we have a self-injective algebra, then we have the stable category, which is triangulated. The suspension is the co-syzygy functor, and we'll write S for the sort of the subcategory of semi-simple modules. We can write that as add A mod J. And recall this notation. So for two subcategories of a triangulated category, we can write A star B for the collection, the subcategory of all objects C that fit into the middle term of an exact triangle with n terms in the subcategories A and B respectively. So using this, we can give a very nice characterization of the subcategory of the stable category of all modules with an SSH resolution of length at most D. And it's going to be this sort of extension category where I have to check what let's forget what this starts with. It's going to start with a D plus 1 of S and all the way down to sigma squared of S. Let's see, they call this XD. So it's just the extensions of the shifts of basically the simple modules. And as a corollary, right, we can say that every MA has an SSH resolution if and only if mod A is equal to one of these subcategories, but we can also shift this subcategory by sigma to the -2 or by and simply write it as sigma D minus 1 S star down to sigma S and star S at the end. So I don't know, this is a very interesting condition which we could look at more generally in other triangulated categories as well, where I don't have a good term for this, but we could say this subcategory of simples S seems to shift generate the stable category. So this is kind of, maybe a different version of a strong generator of a triangulated category. So yeah, I don't know if it'd be interesting to see if this, if something like this has appeared in other contexts, but it seems like an interesting condition to study. All right, so I think my time is up. So I should stop now.
Thank you very much.